So now that we have a decent grasp on how to graph linear relationships using both tables of values as well as our our gradient intercept method, we can start moving on to some of the more abstract questions in this topic. So I've got one here, and this is quite a common sort of trickier, I guess maybe end of the exam type of question, which really requires you to need to understand the concept more than just the procedure of drawing these things. We want to understand what makes a point lie on a line. How can we check for that? So we have gotten used to drawing this stuff. I'll give you a few minutes if you need to pause the video and have a go at graphing this particular linear relationship here, y equals 4x minus 6. But we want to, in this question, check if these 2 points, 1, -2, and 2, -3, lie on this particular line. So I have graphed this line just on Desmos, which is a good tool if any of you use this in school, or if you've never heard of it. It's a really good tool just for graphing your lines here. So I've got this particular line here, and as we expected, it has a y-intercept of -6, and you can hopefully see that on my graph. And it's got a gradient of 4. So for each step in my x direction, each 1 unit in my x direction, I go up 4 units in my y direction. So feel free to draw this on some grid paper and have a look for yourself. You can just verify that this graph is correct. But we want to talk about whether these 2 points actually lie on the line. So going back here, well, how did we actually draw these lines in the first place? Think back to the very first lesson we had in this video series. We drew a table of values. So we went, okay, I'm going to sub in a bunch of x and y values into this table of values, and I'm going to use those to set up a line. And by finding in order to even find the y values, well, we subbed in a bunch of values into the x. So these actually created a bunch of points which we actually plotted on our graph. And you may notice that each of these points and any other ones, for them to lie on the graph, they must satisfy this equation here. So any points that lie on the graph, they need to satisfy this equation. Let me actually write that down because that's a pretty important concept. So points that lie on the line must satisfy the linear equation. So they must satisfy this. And by satisfying, I just mean that, all right, when we put in our x into here and our y into there, it must make this equation true. So we have to have this equality there. We need the left-hand side to equal the right-hand side. Now, if I take you to this graph here, we can actually think of these lines as being made up of infinitely many points, x and y, that satisfy this equation. So you can see as I'm sort of going through here, I've got a bunch of points kind of infinitely close together that join together to make up this line. So to actually check whether these points lie on my line, Well, all I really need to do is just sub in my x into my x, my y into my y. And if my equation's satisfied, then I can say, all right, this point lies on the line because we used the table of values to actually make that line. And we can pick any points in our table of values to make the line. So that means that if a point lies on a line, it can be plotted on a table of values. It can be just plugged into here to get y, and vice versa. And once we are given a point, we just check it by putting it back in. This all depends on my equation being satisfied. So let's actually look at how we can check this. So let's do a check. We're going to check for the point. Was it 1, -2? Yeah. We have 1, -2. I'm going to do a check for this point. So I'm going to write in my linear relationship. So I have y equals 4x minus 6. And I can, from here, just go, all right, well, this is my x coordinate. I'm going to sub that into there. And this is my y coordinate. And putting this in is going to give me a sense of whether the point lies on the line. So back to this little dot point I've made, points that lie on the line must satisfy the linear equation. So plugging these in, I get that -2, so putting -2 into my y coordinate equals 4 lots of 1 minus 2. So let's check this. I have -2 equals 4 minus 2. Or -2 equals 2. But -2 does not equal 2. This doesn't actually satisfy the equation. This isn't a point on the line. So if we actually check this in, if we actually have a look and plug this in, oh, wait a minute. Hold up. We can see a discrepancy here. See, guys, it's okay to make mistakes, and this is a type of sense check that we can do when working through these questions. I've made a bit of a blunder here. I wrote 4x minus 2 instead of 6 here. So checking that, well, actually, I get 4 minus 6 here, and I get -2 on my right-hand side. So because -2 equals -2, that means the equation is satisfied. So my equation is satisfied. So because my equation is satisfied, I can say that 1, -2, this point, lies on my line. And I kind of gave you a little spoiler here, but you can see this point 1, -2. So 1 along the x-axis, -2 along the y-axis. This point A actually does lie on my line. Now let's check this for, we'll call this one point B. So 2, -3. So now we are going to, once again, check for 2, -3. Once again, writing out my linear relationship, y equals 4x minus 6. And I'll actually do this correctly this time. So hopefully we can get a better flow going for some of these ideas. But once again, I'm checking this point lies on the line. So I have a point x, I have a point y. So I can substitute that into there. this into there. And if my left-hand side equals my right-hand side, my point lies on the line. I can make that claim. So here we have -3 equals 4 times 2 minus 6. So next line of working, I have -3 equals 8 minus 6. -3 equals 2. Now, once again, in this case, as compared to my previous point, when I sub in the x and the y values here into my linear relationship, into my linear equation, I get something which doesn't work. It doesn't satisfy this equation because -3 does not equal 2. So therefore, with our mathematical reasoning, well, we can say that my point does not lie on the line. And we can verify this once again on Desmos. And if we look at point B, you can clearly see that that does not lie on the line. It's actually quite a bit off. So we can check our answer. And this is the kind of process that we run through every single time. So we made these tables of values that we can use for any points when graphing our lines. So this idea, sorry, I'll just put a little X here so to show that this point didn't lie on the line. So this concept essentially just works backwards from what we did with using our tables of values to make a line. Now we're saying, well, when given a line, do points lie on it? And the points that do satisfy these equations, so this example here, and the ones that don't do not satisfy the equation. So I can put here the equation not satisfied. So the point doesn't lie on the line. So that, in essence, is how we can check for points lying on our linear relationships, our line graphs. And I encourage you all to use Desmos as much as you can. Just to check your answers, it's a really good tool for working through, especially linear relationships questions. I'll see you in the next video.